Hello, welcome to this massive open online course on Bayesian or MMSE estimation for wireless networks. So, the title of this massive open online course is going to be Bayesian estimation, alright. So, we are in this course, we are going to look at different aspects of Bayesian or basically MMSE estimation, where this term MMSE stands for minimum mean squared error. So, the term MMSE stands for minimum mean squared error. Okay. So, let me write down, because this is something that we are going to keep using throughout the course. It is essential that you familiarize with the nomenclature. This is the minimum mean squared error, and we are going to look at both of these things. We are going to look at both of these things in the context of wireless networks. That is important. That is, we are going to look at examples or applications of both these in the context of wireless networks, especially MIMO, OFDM and wireless sensor networks, correct. So, we would like to look at, in this course we would like to look at Bayesian estimation or minimum mean squared error estimation, especially in the context of wireless networks as applicable to problems involving MIMO, that is multiple input multiple output systems, OFDM, which stands for orthogonal frequency division multiplexing, WSN, which stands for a wireless sensor network. Also, some of you might already be familiar with these terms based on your exposure to different concepts in wireless communications, all right. So, now what I would like to start with is, I would like to start by motivating the need for estimation, or by motivating or illustrating the importance of the concepts of estimation through a simple example, all right. So, first we would like to motivate the relevance of this problem. So, what is the relevance of estimation, especially for wireless communications? What is the relevance of estimation? For that, what we would like to do is, we would like to start by considering a simple example of a wireless sensor network, which we can also abbreviate as WSN. WSN stands for a wireless sensor network. You would like to motivate the relevance of estimation in the context of wireless by considering a simple example from wireless sensor networks. As you might already be familiar from a general understanding, that wireless sensor network consists of basically several sensors, several sensor nodes, which communicate over the wireless channel through a central node, or which is also termed as the cluster head. So, in a wireless sensor network, what we have is basically, we have a central node, which is also termed as the head or the fusion center or the cluster head. We can call this as the fusion center or your cluster head. And what we have other than this fusion center, or we have several sensor nodes, which communicate over the wireless channel. So, what are these? These are basically your sensor and this basically denotes the wireless channel. So, we have these sensor nodes which communicate over their respective wireless channel with the fusion center. They send their measurements to the fusion center over the wireless channel. All right, that's the basic setup of a wireless sensor network, which can basically collates a lot of these measurements from a large number of sensor nodes about some ambient parameters such as the temperature, pressure or other such parameters, and then followed by some processing at the fusion center to come up with an appropriate decision. All right. So, that is the basic paradigm of a wireless sensor node. So, sensor nodes send measurements. So, let us write that down. Sensor nodes basically send or transmit their respective measurements over the wireless channel to the fusion center or basically your cluster head. Okay. For instance, this measurement can be relating an ambient parameter, measurements of parameters such as your temperature, pressure, etc. Okay. Now, what we want to do is we want to start by considering a simple sensor K. So, let us start by considering a kth sensor. So, consider sensor K. Let us model the measurement at sensor K. Okay. Let Yk denote this measurement at sensor K. Now, Yk can be modeled as, and this is the model that is frequently employed, Yk, or this is a simple model that can be used to model this measurement process. Yk equals h plus Vk. I am going to explain these terms subsequently. Equals h plus Vk, where Yk, as we have mentioned, this is the measurement at sensor K. This h is the parameter we are trying to measure, such as your temperature or pressure. This is the quantity that you are trying to measure or basically estimate. And therefore, estimation is nothing but a more scientific term, or one can look at it as a technical term that we are going to use to describe this process of measurement. Any measurement that we make is basically towards estimation of some quantity, such as the pressure, temperature, humidity, moisture content, so on and so forth. All right. And this process, the process of this measurement, all right, the process of this measurement is towards the estimation of a certain quantity, and that quantity, be it the temperature or pressure, etc., is denoted by this parameter h. Okay. And this quantity Vk is another important aspect which has to be explained. This is the noise in the measurement. This is the measurement noise. Okay. Because none of the measurements are ideal, none of the measurements or none of the measuring instruments are infinitely precise. So, what we have is, whenever, even for the same quantity, if we measure it several times, the readings are going to be different because of the noise in the measurement process. All right. So, therefore, this noise in the measurement process, which basically leads to error, or this which leads to deviation of the parameter, that deviation from the parameter h that we are trying to measure. This is basically your measurement noise, all right, and frequently this is modeled as a Gaussian noise, all right. We will come to that later. So, every measurement process, so every measurement model has three key components. One is the measurement or the observation, which is denoted by this quantity yk, the parameter h, that is we are trying to estimate, that is the aim of this measurement process or this observation process, and the noise Vk, which is basically trying to corrupt this measurement process. Okay. So, this Yk is also known as a measurement. We will also frequently call this as an observation, because that is indeed what this is the observed quantity, right. So, this is your observation. Okay, this is the observation, and the h is the quantity or that we are trying to measure. This quantity h that we are trying to measure, this is also known as the parameter. This is the parameter that we are trying to measure. Hence, the process of estimation of this parameter, that is when we are trying to find out what this parameter is, that is the temperature or pressure, this is also known as parameter estimation. All right, and the framework that we are going to use in this course is the Bayesian or the MMSE framework for parameter estimation, that is to basically evaluate this quantity or basically reconstruct this quantity h based on these observations or measurements yk. All right, so this framework is termed as parameter estimation, and that is basically the key to understand what we are doing, that is we are trying to estimate this parameter or parameter estimation. Now, what we have is we have considered a single sensor. So, now consider n sensors, consider n sensors, which means your index k equals 1, 2 up to n. So, we have an n sensor scenario. So, what we have is basically we have a wireless sensor network in which several sensors, n sensors are trying to measure the same parameters such as the temperature or pressure. So, naturally each sensor is going to come up with its own individual measurement, which it is going to convey over the wireless channel to the fusion center. All right. So, these measurements can be modeled as, so the measurement, so naturally I can replicate the model at each sensor. So, at sensor 1 I have measurement 1 equals h plus V1, because they are trying to measure the same parameter, Y2 equals h plus V2, which is a different noise V2, and so on. Yn, this is the nth sensor, equals h plus Vn. So, we have n sensors, naturally we have n observations or n measurements, or more precisely set of, this is a set of n noisy, this is a set of n noisy observations. This is your set of n noisy observations from which we have to estimate this parameter h, and that parameter h is basically, that process of estimating this parameter h is basically termed as parameter estimation. So, these noisy measurements y1, y2, yn are now basically sent by the sensors to the fusion center. So, these y1, y2, yn these are sent to the fusion center, or your cluster head, okay. And from this we have to estimate parameter h, and this process is termed as parameter estimation. This process of estimation of the parameter h from these measurements is termed as parameter estimation. Okay. Okay. Now, there are various techniques for parameter estimation. All right. One such technique is basically known as the maximum likelihood estimation principle, all right, and this is the principle seen in one of the previous courses, all right. In this course, we are going to focus on a separate technique and equally important and powerful technique, which is known as the Bayesian or minimum mean squared error estimation. All right. So, that is basically the title of the course, which is the Bayesian framework, that is how do we use a Bayesian principle or the minimum mean squared error principle for parameter estimation. So, for parameter estimation in this particular course, we would like to use basically the Bayesian we would like to use the Bayesian or the minimum mean squared error. We would like to use the Bayesian or minimum mean squared error principle. All right. Now, what is the Bayesian principle? Now, the Bayesian principle, now any estimation process depends on the probability and probability density functions. All right. So, we have two important components in this process of Bayesian estimation. These two different components are what I am going to list now. The first component that is very important in any estimation process is Py bar given H. What is this? Y bar is basically your vector of observations y1, y2, yn. This is known as the vector of observations or simply as your observation or simply known as the observation vector. Of course, H is the parameter. Therefore, what is Py bar given H? This is the probability density function of the observation vector y bar conditioned on the parameter H. Okay. So, this is the probability density function of the observation vector given the parameter H. So, this is the PDF. Or the probability density function of this is the probability density function of the observation vector y bar given H or conditioned on the parameter H, plus we need another important quantity which is related to the parameter H. This is the probability density function of the parameter H. This is known as the prior probability density function. So, we need two quantities, one is Py bar given H, plus we need another important quantity which is P of H, which is the prior, and this is an important quantity, this is the prior probability density this is the prior probability density function of the parameter H, okay, or the probability density function. So, there are two important components, P of y bar given H, probability density function of the observations conditioned on the parameter H, P of H, which is, and this is unique to the Bayesian estimation framework, that is the prior probability density function of the parameter H, which means we are treating the unknown parameter H as being random in nature, and that forms a key of the Bayesian framework, that is the underlying parameter is random in nature. All right. If you are aware of the maximum likelihood estimation principle, the unknown parameter there is treated as a deterministic parameter. All right. So, hence there is in the maximum likelihood framework there is no concept of a prior probability density function of the parameter H. However, if you are not familiar with that concept, it does not matter. In the Bayesian framework, we assume that the underlying parameter H is random in nature, hence it is associated with the probability density function, that is P of H. Therefore, P of H, this is what this denotes is that this underlying parameter H, is, it denotes the very fact, the important fact that this underlying parameter H is random in nature. And this is something that is important to realize, because this is what distinguishes the Bayesian framework from other similar frameworks, that is the underlying parameter H is random in nature. Now, we would like to use these two quantities P y bar given H and P of H to basically determine an estimate of this parameter H. So, what we would like to do is we would like to basically use these two quantities, the probability density function of the parameter given H, P of y bar given H. This is the observation, this is the conditional probability density function of the observation, the prior, okay. And then what we would like to do is we would like to basically use these to estimate our parameter H. So, these are the two quantities we would like to use to estimate the parameter H. And how do we do that? That basically forms and how do we do that? This process, basically using these two process, how do we do that? That forms the core of your Bayesian estimation framework. That basically forms the core of your Bayesian estimation framework, which we already also said that we are going to consider a specific version of this Bayesian estimation framework, that is your MMSE or minimum mean squared error framework. All right. So, what we have done in this module is basically we have introduced this concept of parameter estimation. All right. So, we have motivated this concept or this idea of parameter estimation as being relevant in the context of wireless communications. Of course, we have seen a simple example in the context of a wireless sensor network, where there are several sensor nodes which are making noisy measurements of this parameter H, and they are conveying these noisy measurements to the fusion center. The fusion center then has to estimate from these noisy measurements, come up with an estimate of this parameter H, and it basically relies on two quantities. One is the prior probability density function P of H of the parameter H, and the conditional probability density function P of y bar given H of the observation vector y bar given the parameter H. Basically, using these two quantities, we would like to come up with the estimate of this unknown parameter H, and this is termed as the Bayesian framework or MMSE, specifically the MMSE, an MMSE part of the Bayesian framework. And this, the unique aspect of the Bayesian framework is that it treats the underlying parameter H as a random parameter, as being random in nature with a certain probability density function P of H. All right. So, we will stop this module here and we will continue with other aspects in the subsequent modules.